geometry. So just first, so in algebraic geometry, what we study is algebraic sets and algebraic varieties. So these will be zero, I mean, at least eventually this is zero sets or sets of solutions of polynomial equations. So we can always write the polynomial equation as some polynomial mean equal to 0. So that means we can write x would be the common zero set of all, say, A1, for instance, n in some field to the n such that f of A1 to an1 is equal to f m of A1 is equal to 0, where, so now this was n, where these fi are some polynomials in several variables. And so it's just
same dimension.
What?
Same dimension? Same number of variables, all?
No. And so the number of variables is always the same, n, no? Because otherwise, how do we put the thing in it? But then we have to say we have m polynomials in n variables. We look at the common zero sets. Okay. And so K for the moment is a field. And so what can one say about this? So for instance, just as some stupid example, if we look at the equation x squared plus y squared is equal to 1 and K is equal to R, we would get a circle. No, an example. But we will usually assume that our field is algebraically closed. So this is basically because otherwise one also has to worry too much about existence of solutions. For instance, if I take x squared plus y squared equal to -1 over the real numbers, it's all of a sudden the empty set. Okay, but we can also, if K is the complex numbers, which one can keep in mind, then this is closely related to complex analysis. And differential geometry. So under suitable assumptions, such a set of solutions to these polynomial equations over the complex numbers will be a differentiable manifold, and one can study with the methods of differential geometry. And one can also consider the case K is equal to the rational numbers, which we will not consider. One comes to arithmetic algebraic geometry. Which is much more difficult. I mean, so this is part of number theory. So one could, for instance, study the equation x to the n plus y to the n is equal to z to the n, with n bigger than 2, an integer, and we want to do this over the rational numbers, as is well known. There will be no solutions in, say, q to the 3, q without 0 to the 3, this statement. So obviously you can always have that, 1 to the n plus minus 1 to the n or something will be, if n is odd, will be 0 or something stupid like that, but otherwise there will be no solution, and this is the Master's theorem. One of the most famous results in number theory, and one of the most difficult also. And so although one has such a stupidly simple equation, it's very difficult to ask whether this has solutions over the rational numbers. Whereas if one wants to describe this over an algebraic closed field, this would be quite simple.
Okay, question?
Yeah.
During the first semester algebra, we say somewhere that the modern number theory is the study of the extension q bar over q.
Well, that's one viewpoint.
It has nothing to do with this.
Oh, it has also something to do with that. I mean, you can, so, you could ask yourself, okay, certainly it's easy to find, to understand the solutions over q bar, and then you have to understand which of those, still come from q. And it's something that, has something to do with how the Galois group acts on these solutions and so on. So it is, in that sense, you can view it like this, and it's used also by if you look at the proof of Fermat's last theorem, which I only did, I didn't do very much. I mean, the only thing is that I know it involves some representation theory of the Galois group, deformations of representations and so on. So some high-tech methods of Galois theory in order to do this, and then relate it to elliptic curves, which is some more standard thing in algebraic geometry. Okay, so this was just some kind of introduction. Now we actually want to start. So first, let me, I have used here polynomials and several variables. As I did not introduce them in the algebra, I will just briefly state a few things. So review of polynomials in several variables. So I don't know precisely where the line is. Here. What? Oh, it's gone. So that's good. Okay. We take a review of one of the variables. So let's say R. Let R be a commutative ring 1. Not be very formal. So we denote Rx, the polynomial ring with coefficients in R. And then we define the polynomial ring in several variables inductively by just the polynomial in 2 variables is a polynomial in 1 variable whose coefficients are polynomials in 1 variable. So we define R x1 to xn inductively as R x1 to xn is equal to, take the polynomial ring with coefficients in a variable xn whose coefficients are polynomial in the other. What does this mean explicitly? So explicitly, the polynomial f in R x1 xn can be written as so f is equal to sum over I1 to In, which are it's a finite sum of non-negative integers, some coefficient I1, In, x1, I1 times xn, In, where these coefficients are in R. So this is called the coefficient of x1 to the I1 xn to the I. So such a just product of powers is called a monomial. So these things are called monomials. And the degree of a monomial is the sum of the powers. So then one can talk about the degree of f. This is the highest occurring degree of a monomial such that the coefficient is non-zero. So which is the largest degree of a monomial x1 to I1 times xn to In such that the coefficient ai1 to In is different from zero. So f is called homogeneous if that the degree of all monomials with non-zero coefficients is the same. So f is called homogeneous of degree E if all monomials with non-zero coefficients have the same degree. If every monomial of f with non-zero coefficient has degree. For instance, if I bring this to the other side, this polynomial is not homogeneous, but its degree is 2. If I would remove this, this would be homogeneous of degree 2. Okay, so this was just this. You see there are a few things to check that this definition gives you this, but you know, that's an easy exercise. Now we want to come to the actual geometry. So we now talk about defined varieties and defined algebraic sets.
Question?
Yes?
In algebraic geometry, when we define varieties, is there a model variety like in differential geometry, like FRN? Is there something like a model and a map that we can define the notion of variety?
Yes, that's. I'm not sure whether we will. So there's different concepts of varieties. You can have defined varieties and projective varieties, and there's also the concept of an abstract variety, which would correspond to somehow to an abstract manifold. But it's that is somehow more general in some sense. So an affine variety is a zero set, as I wrote here, of some polynomials in k to the n. And the variety is something which locally looks like that. So which has an open cover in a very big topology, such that all the open sets are such affine varieties. But this, I'm not quite sure whether I will do abstract varieties because it's a somewhat general concept and it's a little bit complicated to handle. The most important ones practically are the affine and the projective ones.
No, but I mean, like, there is no concrete model space that we can directly compare it with the. Like, for example, in differential manifold, we say that it's differential manifold if it's locally looks under some maps like Rn. So
No. It locally looks like an affine variety. It's much more general locally.
Okay.
So there are model spaces, but there are many model spaces. It has to locally look
it's not a unique model space.
Yeah. Okay. And so that is, that makes it in some sense more difficult or whatever than differential geometry. So let's look at affine varieties. So as I kind of said, we will always assume that K is an algebraically closed field. Maybe sometimes we will assume it's characteristic 0, but not for now. And so first I use a few definitions. So first, in algebraic geometry, for some reason, we give a name to just k to the n. So definition, find n space is an, which is just defined to be k to the n. So this is just a set of a1 to an. Is ai. Okay, it's just standard. Okay, so a polynomial f in variables, so k x1 to xn, defines the function from kn to k. Which I give the same name, f from an to k. In the obvious way, we just replace the variables by the coordinates and do the operations. So p equals to a1 to an descent to f of a1 to an. So this just means, now here stupidly I called it A, but assume it was called P, then I would here say f of A is just this where the x are replaced by this, and then I evaluate this in K. So this is straightforward. So therefore, this defines me a function, so therefore I can look at the zero set. So I use this. Sometimes one calls it the vanishing set and writes V, but I prefer the Z. But in literature you often find also the V. So Z of f is equal to the set of all P in an, such that f of P is equal to 0. Okay? So if I take a set of polynomials, so if we take a subset of the set of polynomials, we can look at the common zero set of that. The zero set is just Z of S. So it's the common zero set of all elements in S. So this is the set of all p in AN such that f of p is equal to 0 for all f in S. Okay? So one can, if you want, look at the solution, simultaneous solution of a number of polynomial equations. And these are the sets we want to consider. The set of this form is called a fine algebraic set. So, subsets of the form C of S in AN are called define algebraic sets. So for a moment we want to study defined algebraic sets. What?
The S is not assumed to be finite?
No. In the moment it's not assumed to be finite. Later we'll see that we can assume it to be finite. And then we get the same result. But that's a non-trivial algebraic statement. It's just any subset. So just as examples. So for instance, AN, the whole of AN, we can obtain as a zero set of the zero polynomial, or as a zero set of the empty set of polynomials. So if I just have a finite set I just write of polynomials, I just write the polynomials here instead of the brackets around. Okay. And the empty set I can write as a zero set of the constant polynomial 1, because that's it, or obviously also as a zero set of all polynomials. No? So these are some simple examples. If we take a point, so P equal A1 to AN, if we have a point like this, then it follows that the set P is also an affine algebraic set. Namely, I just have to say that each coordinate is equal to this. So that means it's equal to x1 with zero set of x1 minus a1 until xn minus an. Because this precisely means it consists of all points in an such that the ith coordinate is equal to ai. There's only one such point, namely this one. You can also look, for instance, some hypersurface, some event if it takes 3 of y squared minus x. If we now for the moment still assume we are over the real numbers, this is a parabola. Obviously over the complex numbers it's a little bit more difficult to imagine, but then it would look somehow like this. This is the y-axis, this is the x-axis. And you can also look at something else. For instance, y squared minus x to the 3. That will die. Yeah, this will somehow now I turn this the other way around. Anyway, so this will then maybe look like this. This is a cuspital cubic. Somehow at this point something special happens. It has some kind of over the real numbers it will look like this. So we can look at many such examples. So if we just take the zero set of one polynomial, we call it a hypersurface. So as you can see, if I don't have so many coordinates, so many variables, I call them x, y, z. And then if I have more, I call them x1 and so on until xn. So if f in k x1 to xn is a non-zero polynomial, non-constant polynomial. A non-constant means it doesn't just consist. It has some monomials with non-zero coefficients of positive degree, and then we call ZF in En plus 1, in En a hypersurface. Okay, so this was just examples. Now we want, so until now there's not so much algebra except that we talk about these polynomials. Now we want to see that one can use some algebra to study these sets, and the first that we want to see is that every affine algebraic set can be obtained as a zero set of an ideal in kx1 to xn. Then we can study them in terms of ideals. So, let's see every affine algebraic set x in An is the zero set of an ideal in kx1. And takes almost longer than to state than to show. So if I have a set S in kx1 to xn, we can look at the ideal generated by S. So let S, which is defined to be the sum of all linear combinations, sum I equals some finite linear combination, 1 to L, AI Fi, where L is some non-negative numbers, can be any kind of number of summands. The AIs are some polynomials, and Fi are our elements in S. So this then is the ideal generated by S. Obviously, the ideal in kx1 to xn generated by S. And then we want to see that the zero set of an ideal, the zero set of a set of polynomials is the same as the zero set of the ideal generated by that. And this is quite simple. So lemma. So the first statement is if I take S and T, so let's say if S is contained in T in K x1 to xn, then the zero set of T is contained in the zero set of S. And this is completely obvious if you think of it, because every element, the zero set means it's a point where all these polynomials vanish. If I take less polynomials, the set where they vanish becomes bigger, and vice versa. So this is clear. And now, the second statement is that if I take the zero set of such a set S, this is the same as the zero set, the ideal generated by S. Okay, and this is also relatively clear. So clearly, the zero set of S contains the zero set of the ideal generated by S. Because S is a subset of S. So thus we only have to see the other inclusion. Conversely, you take a point in the zero set of S, and you have to see that it is also in the zero set of the ideal generated by S. So we take any polynomial in the ideal generated by S, G equal to sum I equals 1 L AI Fi in elements in S. Obviously, the Fi are elements in S and the AI elements in X1 plus N. Then, what is G of P? So, we know that evaluation of polynomials, at the coordinates is just, it multiplies up. So this is just sum I equals 1 L AI of P Fi of P. And this is 0. Because we are in the zero set of S. And so this is 0. Okay, so this is simple. So we want to now, to some extent, use this, anyway, we want now to introduce a topology on a fine space, which is a slightly strange topology, but anyway, it is a topology whose closed subsets are the fine algebraic sets. Okay. So see later that this has a number of crazy properties, but on the other hand, it turns out to be a practical language, because once you have a topology, you can talk about continuous functions and things like that, and it just turns out to be practical. One only should keep in mind that we are not really doing very much topology. I mean, it's just a language, but it's a useful language. So it's a risky topology. Oh no. So this is Zariski. So should I spell it maybe once? It's a name of a person. So Z-A-R-I-S-K-I. So after, after Oscar Zariski, an Italian mathematician of Polish origin, I think, who invented this. And so okay, so how does it go? So basically the statement, so we want to, this is a topology on AN whose closed subsets are the affine algebraic sets. So basically, so in order to talk about this, we have to make sure that such a topology exists. That this kind of description defines a topology. And this is contained in the following proposition. First, if I have if S alpha in some index set is a family of subsets, alpha family of subsets of the ring of polynomials, then if I take the intersection of all alpha in A of the zero set of S alpha, this is the same as the zero set of the union over all alpha in S alpha. And the second statement is if I have now instead two subsets, so if S and T are sets of polynomials, then the zero set of, I take a zero set of S union zero set of T. This is the same as the zero set of what I could call S times T, where S times T is just a set of all products of one element in S and T. And note that this says these two together say thus arbitrary intersections, and finite unions of a finite algebraic set. Are finite algebraic sets. Because the first statement directly says that arbitrary intersections of affine algebraic sets are algebraic sets, and this says that the union of two affine algebraic sets is an affine algebraic set, and therefore by induction any finite union of them is. Okay. And
can we generalize this for union?
No. For arbitrary unions, no. If you take, a point is an algebraic set. So if you take an arbitrary union of point, is any subset. If it would hold for arbitrary unions, it would mean every subset of the fine space is an algebraic set. We certainly don't want that, and it's also not true.
Yes, but what would be the problem if we consider the set of all the finite product in each? So we take a family of algebraic variety, and we take the zero set of all the finite product of those sets.
No, but I mean, in order to get the union, you would have to take the product of all polynomials. And that involves infinitely many polynomials. It's an infinite product, and therefore it's not a polynomial if you can even make it to exist. Okay. So you wanted to obviously use the, but yeah, no, this argument you cannot do infinitely many times because you cannot multiply infinitely many polynomials and then think you have a polynomial. But okay. So now. So the first statement is basically obvious. I can write it here. So if I have a point which lies in the intersection of all alpha of the zero set of alpha, this is if and only if f of p is equal to 0 for all alpha. All f in S alpha. But this is the same as saying that f of p is equal to 0 for all f in the union over alpha S. So this is just rewriting. So these two things are essentially by definition equal. And the other one is not so much more difficult. So now, so the second statement. So first, this inclusion, no, this one. So P, so let P be in this union. And we take F an element in S and G an element in T. And then it follows that F of P is equal to 0 and also G of P is equal to 0. So thus F not F of P is equal to 0, so it's supposed to be the union of the two 0 sets. So therefore, one of the two must be 0. F of P is equal to 0 or G of P is equal to 0. So thus it follows that if I take F times G and evaluate P, this is just F of P times G of P is equal to 0, because one of the factors is 0. And so, therefore, this is true for any F and S and any G and T. So, and for any product we get at 0, so it means that P is in the 0 set of ST. And conversely, let P be in the 0 set of ST. And we assume, so we have then to show it's in the 0 set of S or in the 0 set of T. So let's assume it's not in the 0 set of S. Then we have to show it's in the 0 set of T. So if it's not in the 0 set of S, we can therefore find an element F in S which doesn't vanish at P. So then, thus, for all G in T, we have that F times G of P is equal to 0, because this is an element in ST. So, but this is equal to F of P times G of P. And F of P is different from 0. Therefore, as this polynomial, obviously, if these are just elements in K, so if the product is 0, one of them must be 0, thus it follows that G of P is equal to 0 for all G and T. Okay, so this was, in other words, P is in 0. So as you see, these are very simple verifications, but now this now shows that these affine algebraic sets are indeed the closed sets of the topology on A. First, maybe briefly review just the words. It's not so long ago that you had them, but just use a few of them. Okay, so I want to remind you. So a topology on a set X is a collection of subsets called open subsets. Such that the following holds. Certainly you should remember it. So first, the empty set and the whole of X are open. Second, finite intersections of open sets are open. And third, arbitrary unions of open sets are open.
I never understood why they add the first one. We can only do 2 and 3, are they not? In that term. Because if we take the
Okay. I mean, you could say that, yeah. But I mean, it just makes it easier to. Okay.
Yeah.
Let me see. You take the empty
set, and
set.
if we take the intersection of any family over the empty set, is everything, and the union over the empty set is the empty set.
Yeah, that's okay. But I mean, somehow it's only. I think it confuses the issue to try to minimize the number of axioms. You know, like this, one understands what's going on. Obviously, it's true that one can leave this one out, but it's kind of, you know, I think it's. I find the definition easier to understand like this. Okay, but it's good. So if we have a set with topology, we can also talk, and we have the open sets. We can also talk about closed sets. So a subset A in X is called closed if its complement is open. So therefore, it's clear that instead of giving the axioms for open sets, we can also make the axioms for closed sets, because so thus we so equivalent actions for closed subsets. So we can define the topology by saying what the closed subsets are, because then the complements are the open subsets. And so the equivalent axioms are first, again, if you like it or not, the empty set and X are closed. No? The empty set is a complement of X, and X is a complement of the empty set. Then finite unions of closed subsets of closed sets are closed. So if you the complement of a union of subsets is the intersection of the complements, and the arbitrary intersections of closed subsets are closed. Again, that's the statement, that's the restatement of the number 3 here. So if X has topology, it's called a topological space. And we can talk about such things. So, for instance, the closure y bar of y in X is the smallest, is the intersection of all closed subsets containing it. And so that's a closed subset. And therefore Y is called dense in X if its closure is equal to X. And we can, so these are just some words we want to just use. And so we also will always want to use the induced or subspace topology. So for subset Y and X, the induced or subspace topology on Y is the one whose open subsets are the intersections of Y with the open subsets of X. We are mostly so interested in the closed subsets, and equivalently therefore has closed subsets sections of Y with closed subsets of X.
A question.
Yeah.
Is the unit disk dense with this Zariski topology in R2?
Yes, certainly. Yeah, it will certainly be dense. In fact, you know, the integers will be dense, or it's a, you know, it's a very coarse topology. You know,
It has many open closed sets.
what?
It has many open closed sets.
But it has very few closed sets, and they are very big.
Yeah.
Yeah. Okay. So yeah, you see that it's not so. Okay. And so also a map f from x to y of topological spaces is called continuous. If assume an inverse image of an open subset is open, of every open subset is open, or equivalently the inverse image of every closed subset is closed. And now we already said we get the heuristic topology by taking the closed subsets in fine algebraic sets. So
actually, in R2 the algebraic sets are all bounded, right?
No.
It can be.
Yeah, they certainly go to. I mean, in fact, you can show, let me see whether I can say correctly. No, but in R2 is one thing, but if you work with complex numbers, you can show that if they are not finite, they cannot be bounded. Okay, so it's almost the opposite of what you say. If you have a closed subset of C to the n, the Zariski topology, which is not finite, then it's not bounded.
No, I mean, when you take an algebraic set,
Yeah.
I asked about the algebraic set, the set of zeros of this common polynomial.
Yeah.
It can be not bounded.
It can be not bounded, and I say essentially it has to be not bounded, unless it's what?
It's always not bounded?
Well,
if S is...
Over the complex numbers. It will not be bounded. Over the real numbers, you can have a circle or something like that. But over the complex numbers, it always goes to infinity. Unless,
for example, this z1 square plus z2 square is not just S3? The three-dimensional sphere?
No.
Ah, yeah, this is without multiplication.
No, they,
Sorry. Yeah,
So-
sure.
okay, so they will always somehow.
And then R2?
What? No, R2 it can happen. Obviously, you can, for instance, you can have a circle or something like that. Or also, S3 is also an algebraic set in R2. But they, we only work over the complex numbers, or an algebraic closed field. So the Zariski topology definition. The Zariski topology on AN is the topology whose closed subsets are, I don't know where I write it, are the affine algebraic sets. Okay, and we have essentially seen it's a topology, so we have seen that finite unions and arbitrary intersections are of affine algebraic sets are affine algebraic sets, so that according to this shortcut makes it a topology. But at any rate, we have also seen that the empty set as a zero set of the polynomial 1 and the whole of AN as a zero set of the zero polynomial are also affine algebraic sets. So we have seen this. Okay. We have shown this is a topology. And so, if X in AN is a subset, we give it the induced topology. Which we could call, which then will be called the Zariski topology. On X. So obviously this is particularly, we want to do this in the case when X is itself an affine algebraic set. So by definition, the induced topology means that a closed subset of X is the intersection of X with a closed subset of within a affine algebraic set. But so if X is an affine algebraic set, we see that the closed subsets of X in the Zariski topology are the affine algebraic sets. Y in AN, which are contained in X. This is because, if aurora, these should be the intersections of X with the with the closed subsets, with the affine algebraic sets. But we know that the intersection of any two algebraic sets is an algebraic set, so they are actually.
So particularly in the case of R2, for example, this topology is a subset, is a subtopology of the Euclidean topology, right?
Yes, but I mean, I'm not really interested in the case of R2. No, for me, I always look at algebraic closed fields, so you can say maybe C2.
Yeah.
But yeah, it's coarser than the Euclidean topology. I mean, it's you can just look at a couple of examples, get some idea. So first, all finite subsets of AN are closed. That's clear, no? Because points we have seen are closed, they are finite algebraic sets, and then finite unions of points are finite sets. So this is clear. But on the other hand, if we just look at A1, so the closed subsets of A1 are basically just these R. I mean, we have to have the empty set A1 and the finite subsets. And the finite sets. So there are no others. And so why is that? So if I have a closed subset, it's a zero set of some idea. So that I in Kx in ideal. So if I is the zero ideal, obviously its zero set is the whole of A1. Otherwise, if it's not a zero ideal, it contains a non-zero polynomial. So otherwise, let F be a polynomial in I, which is not zero. And then the zero set of I is contained in the zero set of F, because F lies in I. And so the set consisting only of F is smaller than that of I, so the zero set is bigger. And this, you know, if I can say, I don't really need to do this, but if I, for instance, use this algebraic close the splits into linear factors, I can write this as x minus a1 to the n1 times x minus an a r to the nr, but split it as a product of linear factors, and so okay. So I write f equal to x minus a1 to the n1 times x minus a r to the nr, splitting into linear factors, and then it follows that z of f is equal to the set a1 to ar. So the zero set of one polynomial will always be a finite set. And if I have a zero set of some ideal which contains polynomials even smaller, so it's a subset of a finite set. So it's either empty or it is, you know, a smaller non-empty finite set. Okay, so we see in particular that this topology is very far from Hausdorff. Now on A1, so for instance also well, this is with the complex numbers, this is really the whole complex numbers, and the open subsets are the complements of the finite sets, so all huge, and they certainly don't separate any reasonable separation actions. You cannot separate any 2 points or anything else by open sets. Every non-zero, non-empty, every non-empty open set is dense.
For this argument, do we need the fact that I is an ideal?
No, not really. Just to say it fast. So I could say, no, I mean, I could do a subset, then, you know, either the subset, you know, consists of 0 or it's the empty set or whatever. I mean, you know, there are slightly more cases, but the argument is precisely the same. Well, it doesn't need an idea. It's just that I want to save 5 seconds. Okay. So now we will. Okay. So now we want to. So we have seen that every defined algebraic set is a zero set of some ideal, but the there can be more than one ideal whose zero set it is. And but there's one which is kind of canonically associated to this affine algebraic set, which is just the idea of all functions which vanish on the set. And now, as it's so closely associated to the affine algebraic set, one expects that the properties of the affine algebraic set are reflected in the properties of the ideal. And so we will want to see that. So we'll talk about the ideal of an affine algebraic set. So what's that? So as I said, so let x in En, in fact I can do it for any, to begin with I can do it just for any subset, although we will finally mostly be interested in affine algebraic set. So x in the N is a subset. So we note that. And subset. And the ideal of x is I of x, which is defined to be the set of all f or polynomials which vanish at all points in x. Okay. So we mostly are interested in the case that x is an affine algebraic set. So I maybe can just as an exercise, I might also do it later myself, but I just state it. So maybe I first make a remark. So clearly, if x is contained in y, then it follows that the ideal of x contains the ideal of y. Because we have more conditions, the smaller x is, the less conditions we have for the polynomials f, which have to vanish on x. And as an exercise, I can state that if I look at the zero set of the ideal of x for any subset x in the N, I claim that this is the closure of x. So in particular, if x is an affine algebraic set, then the zero set of ideal of x is equal to x. Because if it's an affine algebraic set, it's closed, and so therefore it's equal to its own closure. Anyway, I think I will do this later anyway, but just to see this would be easy to see. Okay. Now we will use this to come to our first little theorem, which is the Hilbert-Bayes theorem, which answers your question. Namely, we can every affine algebraic set can be obtained as a zero set of a finite set of polynomials. this what is the importance of this result is more general, Hilbert basis theorem. So we want to see, so we have, we know, what? So Hilbert is David Hilbert?
No. I mean, generally in books, it's called Hilbert and some word in German.
No, that's another theorem.
Oh, that's another one. No.
Yeah. This is the easier one. So there's also the Nullstellensatz, which we will get later,
Yeah.
which means the theorem of zeros. But this is the Hilbert'sche Basissatz, so Hilbert basis theorem, which is this. So the Nullstellensatz for some reason is not translated. You take the German word, but here you take the English word. It's just the way we do it. Maybe, I mean, the Nullstellensatz is a bit more scary, so it can also have a more scary formulation. So we know by definition and define algebraic set X in the N is the zero set for S is subset of this set of polynomials, and we want to see S can be taken to be finite. And we show this, we know it is, I mean, the argument is quite simple. So we know that, the zero set of S is the same as the zero set of the ideal generated by S. So we know this affine algebraic set will be a zero set of some ideal. And then Hilbert basis theorem says that every ideal in Kx1 to Xn is finitely generated. And we know the zero set of an ideal is the same as the set as the zero set of the ideal generated by some elements is the same as the zero set of these elements. And so we could take just these finitely many elements which generated. Okay, we come back to that. So we want to show that every ideal in Kx1 to Xn is finitely generated. We need to first need a bit of algebra. We also already know this from somewhere else. So
We
I
did
have
that
to.
for one variable, right?
What?
We did that for one variable. We said that it's principal.
We want it for arbitrarily many variables, but we make some kind of induction.
Yes.
Which, so that in a suitable sense we need for one variable, but then for this being a ring. Okay? So lemma definition. So that R be a ring. So the commutative ring 1. The following are equivalent. First, every ideal I in R is finitely generated. And secondly, if I have an ascending chain of ideals, that means I have an infinite sequence of ideals, always one contained in the next, then after some point they have to be all equal. So R satisfies the ascending chain condition so every infinite chain I1 containing I2 containing I3 and so on of ideals in R becomes stationary. That means from a certain point onwards, all the ideals are the same. There exists an n such that I n equal to I n plus 1 is equal to and so on. Okay? So if you cannot have, they cannot get bigger in infinitely many steps. Okay, now we'll have to prove that these are. And a ring with this property is called Noetherian. These properties is Noetherian. After Noether, who introduced this. Okay, so let's prove this equivalence. So assume we have a chain of, so we assume that our let me see. Yeah. So we assume that our ring is finite, that every ideal is finitely generated. So assume 1. And we take a chain of ideals. Then we can take the union. So that I is the union of all I. Now you can easily see that I claim, so I is an ideal in I. Because this follows directly from the definition. I mean, you need that the sum of any two elements lies in it, and the product with any element in R. But if you take any element here in this union, it lies in one of these, and these things are ideals. And so if I take two of them, then it lies in the bigger one of the two, and so the sum lies also in the bigger one of the two, because they are one contained in the other. And if I have an element which lies in one of them, and I multiply it by an element in R, afterwards it will lie in the same. And so if I take any element in the union, so therefore I, the union of all of them, is an ideal. Well, this is essentially by definition. So thus it is finitely generated. Ideal generated by F1 to Fn to Fi elements in I, but these are finitely many elements which lie in the union of these. So this is just the union of all of these. Each of them must lie in one of them. So there will be a last one in which they lie. So all of these already lie in some, say, IM. No? I mean, this F1 lies in I M1 and so on, and in the biggest one of all of them they lie, and so therefore, so thus this element I is equal to IM, so IM is some number, and so therefore this will also be equal to IM plus 1 and so on. So the last one is, so I need only all of these line 1 elements, so afterwards they cannot come bigger anymore. Okay, so this is this Unitarian, so I have to show the other direction. That's even easier. So now we want to show that if I have an, we prove this by contraposition, so we take an ideal which is not finitely generated in our ring, and we use this to get an infinite chain of ideals. So that I in R is an ideal which is not finitely generated. So then we can just take, so first we take some element F0 in I, then we take F1 in I without the ideal generated by F0, and inductively we take F, say n plus 1, an element in I without the ideal generated by F0 until Fn. We can do this because whatever we know that I is not finally generated, so regardless of what finite demanding elements we take from I, we'll never get the whole of I. We can always choose further on. And so, and thus, F0 contain F1 and is strictly contained is a chain of ideals which does not become stationary. Okay, so now we come, so this was just introducing these Unitarian rings. Now we come to the actual Hilbert basis theorem. Let R be a Unitarian ring. Then if I take R, the polynomial ring, say with n variables, is also Unitarian. So as a corollary, we get that K, if K is a field, Kx1 to Xn is Unitarian. And in particular, every ideal in Kx1 to Xn is finally generated, every define algebraic set X in the N can be written as a zero set of finitely many polynomials. Z X equal to Z of F1 to Fm with the Fi in K x1 to x, the finite set of polynomials. And so this is, first, this is Noetherian because K is Noetherian, because the only ideals in K are 0 and the whole of K. And so certainly there you can't make very long chains of ideals with this. And then therefore every ideal in Kx1 to Xn is finitely generated, and as a zero set, as X is a zero set of some ideals, this ideal is finitely generated, so I can take the generators of the ideal. Okay. There was, I don't think maybe, I mean, it's not quite 1.5 hours because I started slightly late, but I think I will maybe use this another time, because now to start this proof and then finish in the middle of it wouldn't be so nice. So I will start with the proof of this statement the next time. So, thank you.